Hello there, WINDPOWER students, Dr. John Schrage, and it's Christmas time at the Schrage house. We got the tree up. We have 3 trees actually in our house because we love Christmas decorations and I have 2 small kids. And the lights are up around the neighborhood, and we've got a crackling fire going, and we've got hot cocoa brewing, and this all seems pretty energy intensive, and I live in southern Indiana. This is coal country. Everybody's grampy worked in the coal mines. There's no subsidies for any kind of alternative energies in this part of the country. We had to get all our energy from coal. There are literally no nuclear power plants in Indiana. There is literally no commercial production of electricity by wind in Indiana. Wow. Sounds like I live in one of the places that really needs to make a bunch of changes, and frankly, I'm one of the people who needs to make a lot of change if we're going to be changing to renewable sources of energy, and yet it's hard to imagine how that's all going to work. What's it going to take? What would it actually take to change our society over to relying on these kinds of cleaner power or alternative energy, or whatever you want to say, renewable sources of energy? And this is a little bit tricky of a thing for me to give a lecture on because, frankly, in many ways, you guys probably know more about this than I do. I mean, you're energy majors. I'm a humble meteorologist here, but let me tell you what I've learned over the years from seminars and things like that, and you can put that into the context of the things you've learned in your other courses. I mean, one of the things we know is that there's actually a lot of reason to be afraid for the future, in particular when it comes to things like the environment. Now, this is not the kind of class where we're going to start enumerating all those kinds of problems. In the course context of energy, though, there's one very specific problem, and that is that the total energy needs of the world are just growing and growing and growing with no signs of slowing down in the foreseeable future. The particular graph that I'm showing you there and those projections I found in the International Energy Outlook for 2016, which is published by the Energy Information Administration. I only point that out to you because that's a really good and interesting source of information that I feel like I've learned a lot from this semester. Anyway, so if you choose to find it, there's a link right there. This particular chart happens to come from page 7 of that book. I do want to draw your attention to something that I don't mean to be distracting. You might notice that their bar graphs are partitioned there between a red part of the graph and a green part of the graph. All it is that they have separated the contributions to the total amount of energy needed from between 2 different classes of two different groups of countries, members of the Organization for Economic Cooperation and Development and the non-OECD countries. So, I mean, don't get distracted by the colors. It's an important distinction. It's just not important in the context that we're talking about it here. Well, okay, we don't exactly have this exact year on here, but let's just ballpark. Let's say that we will pick the number 600, and if you look at the key here, that's quadrillion BTU. World energy consumption at the present time is running somewhere in the ballpark of 600 quadrillion BTU. BTU is an energy unit. It is not an energy unit that makes me terribly happy. I am a scientist, I think, in terms of the SI system, so I converted that over. That is 6.33 times 10 to the 20th power joules. If you're an energy person and you like to think in terms of kilowatt hours, which I have also done the conversion for there, it's almost 2 times 10 to the 14th power kilowatt hours. That is a lot of power. That is all sources of energy. That is electricity, that is fuel being burned, etc. That is the total, that is all energy sources on Earth, hydroelectric, solar, and so on. That is a lot of energy. And while, again, taking another figure from that energy assessment book, while it's nice to see that the green curve on here is increasing, the fraction of the energy that is being produced by renewables. It's getting better with or without the Clean Power Plan. Let's face it, a lot of our energy needs both now and in the future are continuing to come from sources of energy that are not renewable. And it's hard to see how we can make that work. I mean, there's a lot of questions that come to mind when you see that much reliance on things like liquid fuels and coal and natural gas and so on. I mean, for example, I would wonder can we even extract that much more coal and oil and natural gas from the environment in a cost-effective manner? It passes in and out of fashion to talk about things in terms of like peak oil and so on. But the vague notion that there will reach a point where we have extracted the most oil we can do in a cost-effective way is not a terrible idea, and it's not entirely clear that we can, in a cost-effective way, continue to extract petroleum and coal on those kind of quantities. And for that matter, most of the places where this is being done, like the oil-producing countries and so on, are largely not countries that we particularly like transferring enormous amounts of wealth into. The U.S. has very specific goals about becoming energy independent and so on, or even becoming an energy exporter and so on. But the truth of the matter is we're a relatively large, but just a piece of the world economy, and there isn't a lot of fracking in Europe. There isn't a lot of oil drilling in Europe. They're going to be they're going to be transferring wealth into Russia, and we're going to be transferring wealth into Saudi Arabia and Venezuela and the Niger Delta and plenty of places that we're not sure we want to be sending that kind of money to. Just the process of extracting all those fossil fuels produces an environmental impact. I mean, you have to just look at this business of like strip mining coal or something to know that there's an environmental impact to the processing and extraction of fossil fuels. But of course, there's also the broader issue of what's the impact of adding all of the greenhouse gases associated with consuming all of those fossil fuels. Again, that's not really where this course is going. I welcome you and invite you and encourage you to take ATS 105, the Science of Climate Change, and or ATS 533, Physical Climatology, both of which we talk about in much more detail the problem of climate change and increasing greenhouse gas concentrations and so on. But my guess is you broadly know that in the course of the last 150 years or so, we have been greatly increasing the amount of carbon dioxide in the atmosphere due to the burning of fossil fuels. It is, up several hundred parts per million. It is we're headed towards doubling its pre-industrial concentration and so on. And in fact, as we look forward to the rest of the 21st century, various United Nations groups have created scenarios about different ways in which we could be consuming fossil fuels or switching to renewables or making changes in our economy or whatever, and we get all these projections forward as to how much fossil fuels we're going to be burning and how much carbon dioxide we'll be emitting as part of our greenhouse gas inventory. And on this diagram here, it's not hugely important from your purposes to know like what are the different scenarios here, although my guess is you can tell that biggest curve going up the graph there is the worst scenario where we're emitting the most. But frankly, in none of these scenarios do we ever get back to emitting just as little carbon dioxide as we're emitting now. And right now we're emitting way too much. I mean, even in the most optimistic scenarios, we're in a lot of trouble with regard to the amount of carbon dioxide we're emitting, which is part of the story as to why for the last 100 years or so the temperature of the planet has been increasing. And in fact, will be continuing to increase for the remainder of the 21st century. Again, it's not hugely important for the purposes of this class to know the differences between these different forecasts. They involve different amounts of greenhouse gases and different mixes of fuels over the next 100 years or something. For you to know, I mean, that's not hugely important versus just realizing none of this looks good, okay? We are really relying too much on fossil fuels. We need to get out of this problem here. For all these reasons and more, and again, take ATS 105 and or ATS 533 to learn lots more about these kind of things, we really need to know how to get ourselves off of fossil fuels and onto renewable sources of energy as soon as possible. And that's kind of where I'm going with this lecture. What's it going to take? How are we going to do that? I think probably anybody who's studying the energy major at Creighton probably is at least open to the idea, if not enthusiastic, about solar, wind, biomass, whatever. But what would that take? Is that something we can do? I mean, Lord knows we have a lot of options. We have a lot of different sources of renewable sources of energy. I mean, the gold standard in many ways is solar. And of course we could talk about like hydroelectric, although frankly hydroelectric's got plenty of problems, not only environmental concerns, but frankly there's not a lot of room for growth in hydroelectric. But that's for a different course. Geothermal could be a possibility. Maybe generation of power from tides and waves. That's a thing that exists in some parts of the world. We could talk about things like biofuels and burning of biomass and so on as a type of renewable, carbon neutral, maybe carbon neutral anyway, type of way of generation of electricity. But realistically, in a course about wind power and wind energy, we're wondering about what it would involve with regard to windmills and wind turbines. Now, all of these sources of renewable energy have advantages and disadvantages. Some of them, for example, are more energy dense. They produce more power for the amount of expense, and some produce less, or some involve other environmental impacts. The creation of reservoirs, for example, have a lot of impacts on the ecology of the river that are hard to put a dollar value on, and so on. Solar panels, often some of the designs involve exotic metals that are expensive and not good for the environment when the solar panel has reached the end of its usable lifetime, and so on. There's a lot of issues here. Bats in the wind turbines and things like that. Let's just talk about wind power. I don't want to get in the business of weighing the pros and cons of all these green sources of energy. Let's just talk about wind power and pull back these numbers that we got off of that Energy Information Administration book. 600 quadrillion BTUs, 10.33 times 10 to the 20th power joules. That's the total amount of energy the world needs between all of its fuel sources. And at some finite point in the future, we have to be completely off the fossil fuels. One possibility would be, let's do the wind power thing. And there certainly is reasons to think wind is a great option. Wind doesn't involve exotic technologies that still have to be developed. It's just an economy of scale. We just have to get this whole thing ramped up. Could we do it? Well, I suppose one question you would have to first ask yourself is there even enough energy in the atmosphere to do this? I mean, if we had nothing but windmills, could we produce this much wind power? Alright, well, there's a number of ways we could answer that question. Let's look at the definition of kinetic energy again, way back from literally Module 1 of the course, where basically it's just 1/2 mv squared, or 1/2 mu squared, to use the terminology of this book. I guess one way we could think about this problem is to say, this is the amount of energy we need, right? Let's put that on the left-hand side and say, is there that much kinetic energy in the atmosphere? Or maybe a better way would be to ask, how fast would the wind need to be for the atmosphere to have that much kinetic energy in it? And let's just make sure the atmosphere even has that much, so that we could switch to wind power. Alright, well, off Wolfram Alpha, of all places, I got the mass of the Earth's atmosphere. It's that very large number of kilograms, but we don't actually capture energy from the whole depth of the Earth's atmosphere. We only do it in the lowest, 100, 120 meters, something like that. Let's say the lowest 5% of the Earth's atmosphere, so we're only talking about the lowest, whatever that number is, 2.57 times 10 to the 17th kilograms of the atmosphere. That's the only part we collect energy from. Well, okay, you have the energy you need on the left-hand side, and you have the mass of the lowest 5% of the atmosphere on the right-hand side. Now we can solve for the speed of the wind, and you'd have to have that, if you harvested all the kinetic energy out of the lowest 5% of the Earth's atmosphere to power the Earth, you'd have to have an average wind speed of 70 meters per second, which is like 150 miles an hour. We don't have an average wind speed anywhere near that much. Shockingly, it's not even close. There is nowhere near enough kinetic energy in the lowest 5% of the Earth's atmosphere to power the Earth, in the way we run the economy now anyway. Nowhere near. Now that might come, I'm suspecting you guys are squinting at the screen right now and trying to figure out what went wrong here. But here's the deal. Coal, oil, natural gas, they are the energy of choice at the present time in the Earth's economy for a very good reason. They are incredibly energy dense. The number of joules of energy you can get from a shovel full of coal is really, really high compared to, say, what you can get from a modestly large wind turbine. on your house or something like that. Okay? It's difficult to put enough solar panels on your property to power your house, much less an entire neighborhood. The truth of the matter is, you hook up to a grid and they burn coal by the ton at the power plant, and it powers the whole thing. And it's a lot of coal, but every shovelful of the coal has so much energy. And the same is true with petroleum products. It's not a coincidence that we use gasoline in our cars. Gasoline is ludicrously energy dense. It can move itself, right? The energy you get from the gasoline is more than enough to move the weight of the gasoline and a rather large vehicle and its cargo and so on. It's not a coincidence that we use these things for our fuels. It's also not a coincidence that we need so much of this energy when you think about the fact that we are consuming these non-renewable sources of fuel at a very unsustainable rate. It took hundreds of millions of years to deposit and produce all of that coal as part of the carbon cycle of the Earth atmosphere ocean system. That coal represents energy that was captured by the sun by plants back in the Carboniferous era or some such thing. And now it has been layered into these deposits of coal. That coal seam, which a coal seam might only be a few feet thick, might represent, thousands or even millions of years of captured solar energy deposited in the form of that coal deposit. We're using that up in just a matter of like a few centuries. So, yeah, no wonder we can't just snap our fingers and replace this all with wind. We're using up enormous amounts of the total energy that it's probably not a very large slice of the total energy that has accumulated on the Earth over the Earth's entire history, but it is a large part of what's stored in the form of carbon in the lithosphere, the Earth's crust. When I first ran those numbers, when I was making this lecture, I was pretty sure I had done something wrong. We couldn't be that far off. Surely wind could be a source of power that could replace, if not all, most or something like that of the power on the Earth. So I tried computing this another way. Another way to think about this is that a typical wind turbine averages about 2 megawatts of power at any given moment. They're usually rated around somewhere around 6 megawatts, and they're actually producing about a third of that on average. So, okay, over the course of a year, that many megawatts, that's a joule per second, that's a million joules per second. Actually, a megawatt is a million joules per second. So we could multiply that out by how many seconds there are in a year, and so over the course of the year, you could figure out how many joules that is. And so a typical wind turbine produces about 6.3 times 10 to the 13th power joules, which is a huge amount of power, but that's 7 orders of magnitude smaller than the global energy needed, right? Each wind turbine produces 6.3 times 10 to the 13th joules, and global demand over there on the left is 6.33 times 10 to the 20th power joules. We're off by 7 orders of magnitude, which means that we would need about 10 million wind turbines to produce that total amount of power. Forgetting whether or not there's enough energy in the atmosphere for 10 million wind turbines, that's another story. We would have to make up, just to give you a sense, at the present time, worldwide, there's about 225,000 wind turbines. So we are off by, 5 orders of magnitude here, or something like that, right? There's just nowhere near enough wind turbines to produce the amount. We're not even 1% of the way there. We're not even 1,000% of the way there. We are way too little capacity here. So if we want wind to be a big chunk of our energy needs, one thing we're going to have to do is keep that number about the total amount of energy the world needs under control. And we need to keep it growing, and if anything, we got to reduce it, but guess what? That's not in the cards. Global energy need as population increases, as the technology increases. Again, like in the ATS 105 class or the ATS 533 class, where you can learn about these problems in more detail, you'll find out, as in not only you can in energy courses as well, we're in bad shape on this. We can't control the amount of energy that we're going to need enough to bring this back down into the level where wind could be the solution. So wind power is not going to be the solution here. Wind power has a role, but we cannot just say, I like wind power, let's just keep building turbines and we'll get the world off of fossil fuels. No, it might be part of the solution, but it is not going to solve it. So that makes you then wonder, what could we do? What is a realistic goal of what we could do with wind power as part of our solution to getting off of fossil fuels? Well, maybe there's something we could think about in terms of the costs about these kinds of turbines. Again, I took a little clip here from this website here. I have the URL there if you want to go check these figures out and so on. But at the time of the recording, a good guess as to how much a typical wind turbine costs installed is a surprisingly low, like $3.5 million. Alright, and we'll have typically about 2 megawatts of average production. Well, that's a lot of power, and it's in the form of electricity, okay? Electricity is a challenging source of way to work with energy if you're talking about a vehicle, like a car, and it's not really a source of energy that works at all for like an aircraft, but you know what? How about just household electricity, just ordinary consumer on-the-grid electricity? That's kind of what wind power is good at. Alright, we can use the wind power to produce electricity. Let's see if we could do that. Well, and let's forget about globally. That's a complicated issue. Let's just focus on domestic electricity production. Okay, well, as it happens in the United States, according to the World Bank, we currently consume energy at a rate of about 13,500 kilowatt hours per person per year. Now, that is not counting gasoline, coal, all those kinds. That is just electricity. Okay, that is regardless of whether it was nuclear or coal or natural gas or whatever. But this is not like natural gas warming your house or the gasoline in your car or whatever. Okay, so maybe a possibility is we could get electricity for domestic consumption off of wind. All right, well, if that is the amount of electricity required that is consumed per person per year, we can just multiply that by the roughly 310 million people who live in the United States, ballpark figure there, and you get a total consumption of electricity of that very large number of kilowatt hours, or 4.19 times 10 to the 9th megawatt hours annually. Alright. That means at any given moment you'd have to have, what is that there, about 477 megawatts of electrical production. I'm sorry, 477,000 megawatts of electrical production. Okay, which apparently we can do and can distribute around the grid because we do it right now. Admittedly, we do it mostly with things like coal and natural gas and nuclear and things like that, but apparently this is what we need. Okay. If we were to do that with wind turbines that average 2 megawatts, that works out to about 240,000 2 megawatt turbines. Okay, that is a lot of wind turbines, and they cost about $3.5 million each. You can multiply that through and you get $840 billion. $840 billion to buy enough wind turbines to produce the electricity. We're not powering cars yet. We're not powering jet aircraft. We're just saying the electricity that we need in the United States. Is that something we could do? Is $840 billion a thing? Well, it's hard to put that kind of money in perspective. Let me tell you this. World War II cost a few $100 billion back in 1945. The U.S. contribution to World War II, let's put it that way. The exact figures vary by a factor of 2 depending on what website you're going, but somewhere in the vicinity of like $400 billion is a good guess, of 1945 dollars. That works out to a few $1 trillion in current money. So most of the estimates I saw when I did that kind of calculation put it in the range of like $4 to $5 trillion, which is nothing to sneeze at, okay? $4 to $5 trillion is a lot of money. We spent, that is approximately what the United States spent on World War II. Now, there's a lot of reasons why it was acceptable to spend that kind of money on World War II, from the politics to the geopolitical situation to the end of the Great Depression to, yeah, there's a lot of reasons why it's more complicated than that, but we spent a lot more money on World War II than we're talking about with regard to this wind power solution. So apparently it is not an impossible thing to come up with this kind of money. Just to give you another measure of this, the current U.S. debt sits at about $20 trillion. The federal budget is a little over $2 trillion. This is not a small piece of that, but we have other things that are bigger, and this would have certain payoffs. I mean, these would create jobs. These would reduce reliance on exporting currency to foreign countries, etc. There are reasons why this is not an impossible thing. The bigger issue here is this wouldn't directly help with our fossil fuel problem, because we would still find it challenging to figure out how to power cars using this, or how to cars, jet aircraft, and so on. Okay, there are certain applications where it's hard to see how we're going to get past fossil fuels, and they are frankly a fairly large chunk of the total energy that we need. But this would change the dynamics in terms of the economics of the energy industry. Once this was such a large-scale conversion to the use of wind power were to happen, it would change the economics. And again, I'm not the right person to be teaching the economics, but it would be transferring financing and techniques and technology and personnel from one part of the energy grid to an energy industry to another. And that would make a difference. It would change where investors were putting their money. It would change the cost structure of electricity if it was no longer the buying of the coal that was part of it. Now, this is not without pros and cons. I mean, if you're a coal miner, this sounds terrible. If you are in the business of fracking for natural gas, this sounds terrible, but we gotta maybe think about leadership here. I mean, leadership is about making difficult choices that are for the betterment of others and for convincing people to make sacrifices. And maybe this is something we can do to make changes to the energy industry. But no matter what, we're only talking about electricity in the United States, as our little example there. And we still would have a problem of how would we be powering vehicles. Well, hopefully we would be making changes like electric cars and public transportation, but who knows? Realistically, though, wind is just not enough. Realistically, it's going to take a combination of reduction of the amount of energy we use and a mix or a combination or a balance of a variety of energy sources that, frankly, for the foreseeable decades is going to still require some fossil fuels. It's very difficult to see how we can get past coal or oil or natural gas anytime soon. Especially natural gas is definitely a bridge technology towards green options, well, at least carbon neutral options and so on. Now, nuclear will certainly have to be part of that too, and maybe there's holy grails there, things like fusion and so on, but realistically, a much bigger part of the mix is going to have to be our renewables. Our biofuel, our biomass burning, our geothermal, hydropower, solar power, tidal and wave power, wind power. These are going to have to be the mix of solutions that we are going to use for our sources. But the other side of the story as to what it's going to take if we're going to be switching to green sources, whether that's wind or whether that's a balance, whether we have something equivalent to the New Deal of wind, where we suddenly spend on the order of $1 trillion to put up wind turbines, or whether it's part of a mix of power solutions, we're going to have a better grid. The current transmission grid has a number of problems that make changing to smarter ways of using power and producing power difficult. The key problem, of course, has to do with the fact that the current energy transmission grid has basically no storage. Pretty much as soon as power is produced at a coal-fired power plant or a nuclear plant or on a solar cell, it has to be consumed. There's almost no storage here. And of course that is a problem that then is amplified by renewable sources that have intermittency problems, namely solar and wind in particular. Because if the wind's not blowing, you now have a place where you're not producing any power. If you have your home and it's only on wind power, when the wind doesn't blow and you're off the grid, you aren't having any electricity. Now, if we had some way to store it when the wind was blowing more than you were consuming electricity, and then you could be using that stored electricity, that would be fantastic. It'd also be better if we could transfer energy efficiently farther and so on. But let's focus on the storage issue. I mean, we've mentioned it in an earlier module, there are some situations that work in certain locations, like pumped storage hydroelectricity. If the geography is right, where you have an area where you can make a certain kind of reservoir, you can use excess power when it is not being consumed to efficiently pump water to a higher reservoir, and then the energy is stored in the form of geopotential energy, or that can then be recovered by the use of like a hydroelectric turbine or whatever as the water flows back down when you need more energy. That is only an option, obviously, in certain places. You have to have the capacity to build a significant reservoir right near a lower source, with a significant elevation difference between that and a lower reservoir, like in this case, this large storage facility right above the ocean. But there aren't that many places where something like that is possible. But pumped storage hydroelectricity is certainly a possibility. There are other smart ways that we can make changes to the grid. Again, you guys being energy students probably know more about such things than I do, but I've heard of like the Tesla wall, where Tesla has these batteries that can be programmed to store electricity when it is cheap or available. So you can be, like, for example, during the day, if you aren't consuming that much electricity in your house, but your solar cells on the roof are collecting a lot, you can store electricity in this Tesla wall, and you can then not use that. You can use that power at a different time when you need more than your roof is producing, or you can sell it back into the grid or whatever. There's a number of reasons, like, for example, smart metering, where you could get into a plan where you can buy electricity off-peak cheaply, and then during peak times when the electricity is more expensive, use energy off of your Tesla wall battery thing. This is all very smart. Whether it can scale, whether this can make a big difference or not, that's a challenge, but it's a smart idea. And you probably have seen that there are other ideas that are related. For example, we actually have a lot of storage of electricity out there in the form of car batteries, especially in the form of electric vehicle batteries, which actually already exist and are out there. You can imagine a number of engineers and politicians and so on have thought of this idea where we store electricity in car batteries or electric vehicle batteries or whatever, and then those, much like a Tesla wall, you store energy in there when the energy is cheap or freely produced by your renewable source, and then it goes back into the grid when energy is either whether there's insufficient production from your renewable source or when energy you want to sell it back into the grid or whatever. These are smart ideas. Okay, they can help level the load and make green renewable sources of energy that happen to have intermittency problems better. Another way that you can address things like the need to store energy in the grid is with technology like flywheels, where a large, heavy spinning cylinder is storing kinetic energy, and then during intermittency, you can efficiently extract kinetic energy from the flywheel to generate electricity. There are a lot of studies out there of places where they use flywheels to produce, well, I think it's more accurate to say to deal with intermittency in the power grid in small locations, tropical islands and so on, where like they get a large part of their electricity from maybe wind or solar or something like that. But then during periods when there is a reduction in the electricity available, especially to like critical facilities, they can get the electricity from a flywheel. There are other ways where you can store energy on the grid. There's experiments where they use compressed air, and then when they need more energy, they can release the compressed air to power a turbine. There's, of course, the whole story of the hydrogen economy, where there's a possibility that you would be using excess energy when energy is cheap to produce hydrogen, probably by electrolyzing water, and then later you can use the hydrogen which you've been storing as a way to produce electricity through any of the variety of hydrogen-based technologies, all of which may or may not be able to be scaled to being a global solution, who knows? We're also going to need to be able to transmit power much farther and much more reliably and much more cheaply and much more efficiently and so on. Because no matter what, if we're going to start relying especially on solar and wind, we're going to have to be able to deal with the fact that there's going to be times where there is no available wind power in your area. The wind is not blowing, or there is no available solar. It's dark right now. Clearly, we're going to have to be able to reliably, regularly, on demand, transfer energy across the country. Yes, we have a piecemeal system to do such things now, but we need a much better, well-designed system. None of these problems are going to be easy to solve. That's okay. Okay. Wait till you take a class on global warming and stuff like that. None of those problems are easy to solve. Take a class over there in environmental science. Those guys, none of their problems are easy to solve, whether it's ecology or the economics of environmental issues. It's all a mess. What's it going to take? More than anything else, it's going to take smart people, which is why you guys are studying this stuff. It's going to take a real commitment. We're going to make these things happen. And in relation to the idea to commitment, it's going to take money. And until we're ready to do those things, we're stuck with the energy that we have. But maybe, who knows? But I'm glad that there's smart people working on those problems. Now, as we round up this last lecture here, let's answer a couple quick questions. Question 1. The Energy Information Administration estimates that the usage of fossil fuels like coal, oil, and natural gas will decrease worldwide over the next few decades as economies switch to renewable sources of energy. Is that true or false? Sorry, got a text message there. Make a choice from those two options and get a little feedback before we go on to question 2.